Thank you, Tim. All right, gotta figure out which hand I need here. Okay, yeah, so today I'm going to be talking a little bit about recent lunar bombardment in the last 3 billion years. So this is kind of a standard plot of lunar crater chronology. I had it the right way. So we have the number of craters accumulated over time versus age in billions of years. So what we're looking at here is how the impact rate on the moon has changed over time. And this is constrained by both crater counts on the moon and results from analyses of lunar samples. So there are, of course, many questions remaining, and we've talked about some of these over the last few days. But what I'll focus on here is what, of course, has been the recent impact flux, which is generally poorly calibrated. So for the last 3 billion years, we have very few data points in this section, at least from sample analyses. And so the general assumption has been that this rate has been constant for all diameters. But what I'm going to look at is if it may not have been constant at all for maybe some diameters. So there are some evidence from a variety of analyses that the impact rate may have had spikes in it, especially in this time frame. One is the ages of the formation of asteroid families, which are often thought to maybe be the source of spikes on the lunar, of impact spikes on the lunar surface, and so we see several of these families have formed in this time frame. Also, we see that in the last billion years, both lunar analysis of lunar glasses and ages of meteorites show that there may be more of these forming due to impact in the last billion years. And then finally, analysis back in the 80s by Baldwin show of just the ages of lunar craters themselves show that there may actually be also an uptick in the formation of craters on the moon in the last billion years. So this is continuing on kind of what Baldwin did, but of course with a vastly better data set using LRO data. And with that data, we're determining new formation ages of 42 impact craters greater than 50 kilometers in diameter that were previously recognized as either Copernican or Erastinian. And these were labeled by Wilhelms and the USGS on maps, generally due to stratigraphy and morphology of the craters themselves. So a first step was to measure craters on that are superposed on the floor of these larger craters. So we're looking at the measurement of smaller craters, shown by the yellow and blue circles here. And by small, I mean generally they were less than about 1 kilometer, sometimes up to 10 kilometers. And we use the standard technique of removing secondary craters formed, obvious secondary craters formed in clusters and chains, which are shown by the blue circles. So we have what we thought was the primary crater distribution. We generated the cumulative number of craters per diameter and fit that with the model production function generated by Simone Marchi and colleagues, and to derive a formation age for the larger crater, and in this case for Theophilus we see about 3 billion years. So one of the main assumptions of this work is that these small impactors are actually constant and thus disconnected from the large impactors. So in this case, we're talking about the small impactors that form the small craters that we're counting, the superposed craters that we're counting. So, and this has been shown to be a possibility by Botke et al. Back in 2007, where they looked at the number of impacts that would form from the Baptistina asteroid family at different size ranges. So around 1 kilometer, which would form some of these smaller impactors we're looking at, or smaller craters we're looking at, we see that the number of craters formed during the impact, or from the family, is actually less than what we would expect from the background. So in this case, we wouldn't see a spike of small impacts on the moon. But when you look at the larger impactors forming the craters that we're examining here, you do see that more form from the asteroid family than form from the background rate. So this could result in a spike of crater formation at this size. So as I said, we examined 42 craters. They're located across the surface and range in size from 50 to about 150 kilometers. And so in order to do the analysis, what we start with is we plot the frequency of crater formation ages as a histogram as a proxy for impact flux. So here we see just the craters bigger than 100 kilometers plotted on the histogram, and we see that there actually were none of these that formed in the last 3 billion years. So in order to determine if any that have formed in this last 3 billion years, or maybe not have formed in the case of a lull, we just pull from a random Monte Carlo simulation crater ages within this time frame from this chronology function shown in red. And if we did not see the feature we are looking for, the impact flux that we are looking for, very often in the simulation, so less than 1%, let's say, then there might be a high probability that what we're seeing is either a spike in the distribution or a lull. Certainly it wouldn't be consistent with a constant flux, which is what the chronology function assumes. And then if it was greater, if we saw that feature greater than 10% of the time, then we assumed it was consistent with a constant flux. I just want to talk a bit about the chronology function itself. As I said, in the last 3 billion years, it's assumed to be constant. Before that, it, of course, increases as we expect, but then it drops off, which is not usually what happens. And this is actually just to represent the fact that we have an observational bias for craters older than about 3.8 billion years. The activity on the moon at this time was likely erasing features, erasing older craters, and we're just not able to see them. So just to start to look at the results, as I mentioned, for the greater than 100 kilometer craters, we see that none have formed in the last 3 billion years. So doing this statistical analysis, there seems to be actually be a 95% chance that this means that there was a lull in the crater impact rate. So there should have possibly been at least one crater that formed in this time frame that did not form. Looking at slightly smaller craters down to 90 kilometers, we get 3 craters that have formed in this time frame, and their distribution in this time is consistent with a constant flux. And so going now down to 80 kilometer craters, we have about 6 craters that have formed in this time frame, and there might potentially be a spike in the 1.7 to 1.8 billion year time frame. And however, the probability is pretty low, but overall the number of craters that have formed might actually be more consistent with another lull in this time frame. So once we get to slightly smaller craters, we're seeing a more interesting trend emerge in that what seems to be a very significant spike of craters has occurred in the last about 300 million years. So, and quite a few craters seem to have formed in that time frame. There may be another spike here at about 2.2 billion years ago. You can see this other spike at the other size range is no longer significant. And then there may be a lull until the very recent spike, or there could be a lull between these two spikes if this spike is significant enough. So going down to 60 kilometers, again, we see this very recent spike is still quite significant. There's even, I think, 1 or 2 more craters that formed in this time frame. The spike here at either 1.8 or 2.2 has disappeared, is no longer significant, and but there's a potential lull until this very recent spike. And then finally, getting all the way down to 50 kilometer craters, we again see the trend we saw at about 70 kilometers with this very recent spike, a potential spike at 2.2, and then either a lull to the very recent spike or a lull between the two spikes. So to conclude, Basically, in this illustration here, I show the two kind of possibilities that seem most common, in that we could have a long lull shown by the green leading to a spike at about 0.2 billion years ago, or a shorter lull between the two spikes, one at about 2.2 and then the other one again at 0.2 billion years ago. And as I described at the beginning of the talk, spikes could be supported by other data, such as the ages of lunar glasses. And that what we also see is that different diameter ranges seem to actually have different trends or configurations in their impact flux. And this could potentially be due to how impact families themselves formed and are brought into the point where they become impactors from the asteroid belt. And that would actually be something a bit more for Bill Botke to discuss, and we should probably do that soon. So, but that's it. Thank you.
We have plenty of time for questions. Jim?
How do you deal with auto-secondaries that don't have the classic secondary shape? Do you take that into consideration when you're counting the interiors?
Yes and no. So obviously they're very hard to remove from the data set because we can't recognize them as secondaries. However, I've incorporated into like the error analysis on the ages and stuff like that. So I try to use a very kind of large error on the ages when thinking about them.
Other questions?
Okay. So actually, I have kind of a historical perspective to throw at you, and I have no idea what the right answer is. But, okay, Shoemaker, a long time ago, looking at crater frequency, said there was a big increase within the last 200 million years in impact flux. And then Alfred McEwen, at that time working at the USGS, wrote a paper that said, big impact flux, increasing the impact flux at 200 million years ago. And if I recall correctly, I think Jen may still be here, when Jen Greer was looking at that with Alfred, they made that go away. So we seem to have this history where we get these big spikes suggested within the last 200 million years, and then they go away. So are you confident yours is going to stay?
That is a good question. Somebody once told me they would not bet their life on my crater counts, and I'm pretty sure I wouldn't bet my life on this, but I'm probably betting my career in a sense, so. But yeah, I mean, there does seem to be more than just what I show here that supports this uptick in the last few hundred million years of an increase in the crater flux. And I know even some of the dynamical work with the family formations and stuff like that also seems to point that this is a strong possibility. So, yeah.
Anybody else? Actually, I have a question. So with the first point you have up here in your conclusions, is there additional data set or tweak to a model that can help you differentiate between a long lull or shorter lulls, or do you need samples from specific places? I mean, what kind of helps you suss that out?
That's another great question. Obviously, samples would always help. You know, we have this area that is very non-constrained, basically, by any kind of sample. And so to get either the ages of some of these younger craters or terrains that we know are in this age range could definitely help us pin down better what the smaller crater flux was certainly doing at this time, which would help improve our confidence in these ages. I think dynamically, Bill and I have started talking about, you know, when some of these families have formed, what that might mean for when spikes occur. But that of course has its own set of uncertainties as well. So yeah, I mean, I think samples of course probably would be the best thing.